Let's discuss two problems from the latest Codeforces round, starting with division 1b. You can read it now, listen to my explanation. In my explanation, there is a segment from 0 to m on the number line. There are also n integer points on this segment. Some points may coincide. You need to pick another integer point x on this segment. After that, another integer point y will be randomly chosen between points from 0 to m. You win if your point x is one of the k closest points to this randomly chosen point y among the n+1 points. If there are several points at the same distance from y, the winning points will always be chosen not to your advantage. So if there are k points from the input which are not further from y than your point is, then you will lose. You need to choose such x which maximizes the chance of winning. And if there are several such x's, you need to choose the smallest one. So let's say that the black points are the n points given in the input. And let's say that red point is our point x. Let's see for which y this x is winning. First of all, there can be several points from the input at the same position as x. Let's say that there are p such points. Those p points will never be further from y than our point is. So they will always count as the points not further from y than our point is. Now, if there are k minus p other points which are not further from y than our x is, then we will lose. If p is at least k, then we are guaranteed to lose. So suppose p is less than k, so this is larger than 0. Let's consider two symmetrical cases, if y is to the left of x and if y is to the right of x. Let's consider one of the two when y is to the left of x. Let's find k minus pth point to the left of x in order from right to left. So if this is point 1, point 2, etc., suppose this is point k minus p. I claim that we will win if and only if point y is closer, strictly closer to x than to this point. Because if y is not closer to x than to this point, then this and all those points in between are not further from y than the point x is. And there are at least k minus p of points at those positions, so we will obviously lose. And if y is strictly closer to x than to this point, then only points here are potentially not further from x than our point is, apart from those p points which we've already counted. And we know that their amount is less than k minus p, so we will win. But we must also consider the case when this point does not exist, because there can be less than k minus p points to the left of x. In such case, any y to the left of x will be a winning y for us, because those points are surely further from y than our point is, and those we've already calculated, and there are less than k minus p of those points. So if you consider the case when p is less than k, then if y is equal to x, we will win. And if y is to the left of x, then there are two cases. Either number of points to the left of x is less than k minus p, then we will always win. Or we must look at the k minus pth point from right to the left of x. And if you mark its coordinate as z, then y shall be closer to x than it is to z. So y shall be larger than x plus z over 2. As y is integer, we can say that it's larger than this thing rounded down, or larger or equal than this thing rounded down plus 1. So the minimal winning y for us is either 0 or this expression. Similarly, if you consider the case when y is to the right of x, you will also have two cases. Either there are at least k minus p points to the right of x, then you can name k minus p's of them as t, and in this case y shall be closer to x than it is to t. So y shall be less than x plus t over 2, which is the middle between x and t. So it's strictly less than this rounded up. So it's less or equal than this rounded up minus 1. Or if there are less than k minus p points to the right of x, then y is just less or equal than m. Any y to the right of x will be a winning y for us. So if you name the minimal possible winning y as L and the maximum possible winning y as R, all those y's in between L and R are winning. So the number of winning y's for such x is R minus L plus 1. And L will be one of those two expressions, and R will be one of those two expressions, depending on if there are at least k minus p points to the left of x, and if there are at least k minus p points to the right of x. So this allows us to find the number of winning y's for a given x in log time, because to find L and R, we simply need to find the first point from the input array smaller than x and the first point from the input array larger than x. This can be done using lower bound and upper bound. Now let's consider each point from the input as a possible candidate for x. We will choose which one is the best. But x can be in between two points, as well as to the left of all points or to the right of all points. So let's now consider only the case when x is different from all the points from the input. But now let's see how the answer, the number of winning y's, changes if you move x in between this gap. If x stays in between the same 2 points, or is also to the left of all points, or is also to the right of all points, so its position relative to the other points does not change, then first of all, which one of those two will be L does not change, and which one of those two will be R does not change, because the number of points to the left of such x does not change, and the number of points to the right of such x does not change. And if this is L, then Z does not change, and if this is R, then T does not change, because k minus pth point to the left of x does not change, and k minus pth point to the right of x does not change. So if you change x by plus 2, instead of x, let's consider x plus 2. What changes? In this case, this expression will be larger by 1, and this expression will be larger by 1. So L either stayed the same or increased by 1, and R either stayed the same or increased by 1. Which one of the two events happen does not change as long as the disposition of x relative to the points from the input does not change. So if you keep applying this change to x, if you keep increasing x by 2, but the position of x relative to the other point stays the same, then this answer will always change by the same constant. It may be 0 if both of those events happened, or if both of those events happen. Then the answer does not change if you move x. Or the answer can move by 1 down or by 1 up, if only one of those two events happen. And obviously the opposite change happens if you decide to move x by 2 down. So given that if the answer stays the same, we want to minimize the x, it's always either optimal to move x to the right as much as we can or to the left as much as we can. Given that we changed x by 2 because of this rounding down here and rounding up here, we didn't want to mess with the parity. So given that we changed x by 2, and given that we didn't change the disposition of x relative to the other points, we may end up either right next to this point or by 2 to the left of this point. Or if it was optimal to move x to the left, we could end up right next to this point or by 2 to the right of this point. If x was initially to the left of all points, then we could arrive also here or there, or here or there. And if x was to the right of all points, then we could end up here or there, or if it was optimal to move x to the right, then here or there. So we have proven that it's enough to just consider around 5n candidates for x. Either x is equal to one of the points from the input, or it's right next to it to the left, or it's by 2 to the left of it, or it's right next to it to the right, or by 2 to the right of it. So each point gives us 5 candidates of x. Also, we have to manually consider the case of x equal to 0, x equal to 1, and x equal to m, x equal to m minus 1. So that's the whole solution. Let's look at the implementation. First of all, let's look at the function f which accepts x, the array A by reference, and k and m, and returns the number of winning y's for such x. And the array A must be sorted in advance. I is the index of the first point in the array A, which is larger or equal than x, and j is the index of the first point in the array A, which is larger than x. So points from the semi-interval from I to j will be equal to x. So if there are at least k such points, it means that p is at least k. Then we definitely lose, no y is winning for us. So we return 0. Otherwise, we subtract this p from k. And now, if there are k points apart from those points from I to j, which are not further from y than our point x, then we lose. So we consider the kth point. It used to be k minus pth point, now it's just k, because we subtracted p from k. We consider the kth point to the left of x. If it doesn't exist, then L is just 0. The lower bound for winning y is 0. But if such point exists, we set L to the middle between this point and our x, rounded down plus 1. And the same with the right bound for a winning I. If there are at least k points to the right of x, then we set R to the middle between the kth point to the right of x and x, rounded up minus 1. So I just put minus 1 into the brackets. So it became minus 2 rounded up, right? And to round up, you need to add the denominator minus 1 and round down. So this is the same. And now I just return r minus L plus 1 or 0 if L turns out to be larger than r. Now I read the array A, I sort it, and I form the array of candidates for the answer. It's 0 and m. Then if m is larger than 0, it's also points 1 and m minus 1, as I said. And each point gives us at most 5 candidates. It's this very point, and if it's positive, then this point minus 1, and if it's larger than 1, then this point minus 2, and if it's less than m, then this point plus 1, and if it's less than m minus 1, then this point plus 2. And now I just go through all those candidates, I see the result for such a candidate, and I update the answer with such result. If the answer is the same, I choose the smaller x. And then I output the answer and the best x. That's it.